Our solar system is a vast and intricate dance of celestial objects. At the heart of this cosmic ballet spins the Sun, a star that anchors everything in its gravitational embrace. Around this radiant giant whirl 8 planets, each a unique world unto itself. These planets, along with their moons, asteroids and comets, constitute our cosmic neighborhood. This neighborhood, far from being a static backdrop, is a dynamic system where each member influences the others, sometimes subtly, sometimes dramatically. Understanding our solar system is not merely an exercise in academic curiosity. It's about comprehending our place in the universe. It's about appreciating the delicate balance of forces that make life on Earth possible. And it's about recognizing that the fate of our planet is inextricably intertwined with the cosmic drama unfolding around us. From our vantage point on Earth, the other planets appear as bright points of light moving across the night sky. But these seemingly distant wanderers are far more than just celestial decorations. They are our cosmic kin, forged from the same primordial cloud of gas and dust that gave birth to our Sun. And though separated by vast distances, they exert a subtle yet profound influence on our planet. Each planet, with its unique size, composition and orbit, plays a role in the intricate gravitational choreography of the solar system. Jupiter, the largest planet, acts as a cosmic shield, deflecting or capturing comets and asteroids that might otherwise pose a threat to Earth. Mars, our reddish neighbor, holds clues to the potential for life beyond Earth, while Venus, shrouded in a thick atmosphere, serves as a cautionary tale about the dangers of runaway greenhouse effects. Gravity is the invisible force that binds our solar system together. It's the glue that holds planets in orbit around the Sun and dictates the rhythmic dance of moons around their parent planets. But gravity's influence extends far beyond simply keeping things in line. It also creates a complex web of interactions between celestial bodies, influencing their orbits, rotations, and even their internal structures. The planets, though dwarfed in size by the Sun, exert their own gravitational pull. This pull, while much weaker than that of the Sun, is still significant enough to cause perturbations in the orbits of other planets. These perturbations, though seemingly minor, can have significant effects over astronomical timescales, influencing the long-term stability of the solar system. The influence of our planetary neighbors extends beyond gravity. The Sun, a raging inferno of nuclear fusion, constantly spews out a stream of charged particles known as the solar wind. This solar wind, carrying with it the Sun's magnetic field, permeates the entire solar system, creating a dynamic and often turbulent environment known as space weather. Earth, protected by its own magnetic field, is largely shielded from the harshest effects of space weather, but our planet is not immune. Intense solar storms can disrupt satellites, interfere with radio communications, and even trigger auroras, the dazzling displays of light that illuminate the night sky at high latitudes. Exploring the solar system is not just about satisfying our innate curiosity about the cosmos. It's about understanding our place in the grand scheme of things. By studying other planets, we gain a deeper understanding of our own. We learn about the processes that shaped our planet, the forces that govern our climate, and the delicate balance that makes life on Earth possible. The more we learn about our cosmic neighborhood, the more we realize that Earth is not an isolated island in the vastness of space. It's an integral part of a dynamic and interconnected system, where events occurring millions of miles away can have tangible effects on our planet. Understanding these connections is essential for safeguarding our future and ensuring the continued habitability of our pale blue dot. Mercury, the smallest planet in our solar system, is a world of extremes. Scorched by the sun's relentless heat, its surface is a desolate landscape of craters, cliffs, and vast plains of solidified lava. Yet despite its harsh conditions, Mercury holds a certain allure, a stark beauty that speaks to the raw power of our solar system's central star. Its very existence, so close to the sun's gravitational pull, is a testament to the delicate balance of forces that govern our cosmic neighborhood. Often lost in the glare of the sun, Mercury is a challenging object to observe from Earth. Its proximity to our star means it's only visible for brief periods, low on the horizon, just before sunrise or after sunset. But even with limited visibility, astronomers have been able to piece together a remarkable amount of information about this enigmatic world, thanks to robotic emissaries dispatched to explore its secrets. Mercury's orbit is highly eccentric, meaning it traces out a path that's more oval-shaped than circular. At its closest approach to the Sun, known as perihelion, Mercury comes within a mere 29 million miles of our star's fiery surface. At its farthest point, or aphelion, it swings out to a distance of 43 million miles. This dramatic variation in distance results in extreme temperature swings on Mercury's surface, from a scorching 800 degrees Fahrenheit during the day to a frigid minus 290 degrees Fahrenheit at night. This eccentric orbit, coupled with Mercury's relatively slow rotation rate, creates a peculiar phenomenon on the planet's surface. A single day on Mercury, measured from one sunrise to the next, lasts a grueling 176 Earth days. This means that a single day on Mercury is twice as long as a Mercurian year, which is only 88 Earth days long. This unique day-night cycle, combined with the extreme temperature variations, makes Mercury a truly alien world, vastly different from our own. Despite its challenging environment, Mercury has been visited by spacecraft from Earth, most notably NASA's Messenger mission. Launched in 2004, Messenger spent 4 years orbiting Mercury, mapping its surface in unprecedented detail and collecting a wealth of data about its composition, magnetic field, and tenuous atmosphere. The mission revolutionized our understanding of this enigmatic world, revealing a planet far more complex and dynamic than previously imagined. One of Messenger's most surprising discoveries was the presence of water ice in permanently shadowed craters near Mercury's poles. These craters, shielded from the sun's relentless heat, act as cosmic cold traps, preserving the ice for billions of years. The discovery of water ice on Mercury, a planet so close to the sun, has profound implications for our understanding of how water and other volatiles, essential ingredients for life as we know it, were distributed throughout the early solar system. Though small and seemingly insignificant compared to the solar system's giants, Mercury plays a crucial role in maintaining the delicate gravitational balance of our cosmic neighborhood. Its presence, along with the other inner planets, influences the orbits of asteroids and comets that venture into the inner solar system. These small icy bodies, remnants from the solar system's formation, can pose a threat to Earth if their orbits intersect our planet's path. Mercury's gravitational influence, though subtle, can nudge these objects onto slightly different trajectories, potentially steering them away from Earth or sending them on a collision course with the Sun. This intricate gravitational dance, played out over millions of years, highlights the interconnectedness of our solar system and the importance of understanding the roles that even the smallest players can have in shaping our cosmic destiny. Venus, the second planet from the Sun, is often called Earth's twin. Similar in size and mass to our own planet, Venus was once thought to be a lush and hospitable world, perhaps even harboring life. However, a closer look reveals a planet that is anything but Earth-like. Shrouded in a thick, toxic atmosphere, Venus is a scorching inferno, its surface hot enough to melt lead. Far from being a twin, Venus stands as a stark reminder of how different planetary evolution can be, even between seemingly similar worlds. Despite its inhospitable nature, Venus holds valuable lessons for understanding our own planet. Its thick atmosphere, composed primarily of carbon dioxide, traps heat from the sun, creating a runaway greenhouse effect that has driven surface temperatures to an average of 900 degrees Fahrenheit. The atmospheric pressure at the surface of Venus is 90 times that of Earth's, equivalent to being 3,000 feet beneath the ocean's surface. This crushing pressure, combined with the searing heat, makes Venus one of the most hostile environments in our solar system. Spacecraft sent to explore Venus have had to be specially designed to withstand these extreme conditions, and even then their missions have been short-lived. The Soviet Venera probes, for example, only survived for a few hours on the Venusian surface before succumbing to the intense heat and pressure. Despite the challenges, studying Venus's atmosphere is crucial for understanding the dynamics of planetary climates. The runaway greenhouse effect that has gripped Venus is a cautionary tale, highlighting the potential consequences of unchecked greenhouse gas emissions. By studying the processes that led to Venus's extreme climate, scientists hope to gain insights into how to mitigate climate change on Earth. Though obscured by its thick cloud cover, Venus's surface has been mapped in detail by radar instruments on board orbiting spacecraft. These maps reveal a diverse and geologically active world with mountains, valleys, volcanoes, and vast plains. Unlike Earth, which has plate tectonics that constantly reshape its surface, Venus appears to have a more static crust with geological activity concentrated in specific regions. One of the most intriguing questions about Venus is whether it was always so inhospitable. Some scientists believe that early in its history, Venus may have had a more temperate climate, perhaps even with oceans of liquid water. However, as the sun's luminosity increased over billions of years, the planet's surface temperature rose, eventually triggering a runaway greenhouse effect that boiled away any surface water and transformed Venus into the hellish world it is today. The study of Venus's atmosphere has provided valuable insights into the role of greenhouse gases in regulating planetary climates. The thick carbon dioxide atmosphere of Venus acts like a blanket, trapping heat from the sun and preventing it from escaping back into space. This greenhouse effect is essential for life on Earth, keeping our planet warm enough to support liquid water. However, as Venus demonstrates, too much of a good thing can be disastrous. The runaway greenhouse effect on Venus is a stark reminder of the delicate balance that governs planetary climates. By studying the processes that led to Venus's extreme climate, scientists hope to gain a better understanding of how to mitigate climate change on Earth. The lessons learned from Venus serve as a cautionary tale, highlighting the importance of responsible stewardship of our own planet's atmosphere. Mars, the fourth rock from the Sun, has captivated the human imagination for centuries. Its distinctive reddish hue, visible even to the naked eye, has earned it the moniker the Red Planet, a testament to the iron oxide, or rust, that coats its surface. Unlike the searing heat of Venus or the crushing gravity of Jupiter, Mars presents a tantalizing possibility, a world potentially hospitable to life, or at least a world that might have harbored life in its distant past. This potential, coupled with its relative proximity to Earth, has made Mars the prime target in our search for life beyond our own planet. From early telescopic observations that revealed polar ice caps and shifting surface features to the robotic explorers that have roamed its surface, each new discovery about Mars has deepened the mystery and fueled our desire to unlock its secrets. The possibility of finding even microbial life on Mars would be a profound scientific discovery, fundamentally altering our understanding of life's place in the universe, and perhaps even offering clues about our own origins. Though smaller and colder than Earth, Mars possesses a stark beauty all its own. Vast plains of volcanic rock stretch across its surface, interspersed with towering volcanoes like Olympus Mons, the largest volcano in the solar system, and deep canyons like Valles Marineris, a chasm so grand it dwarfs the Grand Canyon on Earth. The Martian surface bears the scars of a tumultuous past, a testament to ancient floods, colossal impacts, and perhaps even the whispers of plate tectonics, long gone silent. Despite its current arid state, evidence suggests that liquid water once flowed on Mars. Dried riverbeds, ancient lakebeds, and minerals that form in the presence of water all point to a wetter, warmer past, a time when Mars may have been a more hospitable place for life to emerge. Understanding the history of water on Mars is crucial to unraveling the planet's past habitability and its potential to support life today, even if that life exists only in microbial form deep beneath the surface. Today, most of the water on Mars is locked away as ice, frozen beneath the surface or forming the polar ice caps that wax and wane with the Martian seasons. However, recent discoveries suggest that liquid water might still exist on Mars, albeit in small amounts and under very specific conditions. Recurring slope lineae, dark streaks that appear on Martian slopes during the warmer months, have been tentatively linked to the flow of briny water, a tantalizing hint that liquid water might still play a role in shaping the Martian surface even today. The search for liquid water on Mars is more than just a scientific curiosity. Water is essential for life as we know it, and its presence, even in trace amounts, would significantly increase the chances of finding extant life on Mars. Moreover, the discovery of accessible water ice would be a game-changer for future human missions to Mars, providing a vital resource for drinking water, oxygen production, and even rocket fuel. Mars represents more than just a scientific target. It embodies a vision of humanity's future beyond Earth. The challenges of sending humans to Mars are immense, requiring technological advancements in spacecraft design, life support systems, and radiation shielding, to name just a few. Yet, the potential rewards are equally profound, offering a chance to expand our species' reach, unlock the secrets of another planet, and perhaps even ensure our long-term survival should Earth ever become uninhabitable. The journey to Mars will be fraught with risks and challenges, but it will also be a testament to the indomitable spirit of human exploration, our innate desire to push beyond the boundaries of the known and venture into the vast unknown. The lessons learned from exploring Mars, from developing new technologies to understanding the limits of human adaptability, will undoubtedly shape our future on Earth and beyond as we continue our journey of discovery among the stars. As we venture beyond the inner rocky planets, we encounter the gas giants, Jupiter and Saturn, colossal worlds that dwarf the Earth in both size and mass. These behemoths, shrouded in swirling clouds of gas and adorned with intricate ring systems, are more than just distant neighbors. They are guardians of the solar system, their immense gravitational pull shaping the trajectories of comets and asteroids, influencing the orbits of their neighboring planets, and even playing a role in the very structure of the asteroid belt. Jupiter and Saturn are worlds of extremes, with turbulent atmospheres whipped by supersonic winds, colossal storms that rage for centuries, and magnetic fields thousands of times stronger than Earth's. Yet for all their ferocity, these gas giants play a vital role in maintaining the delicate balance of our solar system, their gravitational influence acting as an invisible hand that has shaped the destiny of our planet and countless other celestial bodies. Jupiter, the largest planet in our solar system, is a true giant, with a mass greater than all the other planets combined. Its immense gravitational pull acts like a cosmic vacuum cleaner, drawing in comets and asteroids that stray too close to the inner solar system. This protective shield has earned Jupiter the nickname the solar system's vacuum cleaner, a testament to its role in safeguarding Earth and the other inner planets from potentially catastrophic impacts. Without Jupiter's gravitational influence, the inner solar system would be a far more chaotic and dangerous place. Comets and asteroids, remnants from the early solar system, hurtle through space at incredible speeds, their paths influenced by the gravitational pull of the planets. Jupiter's immense gravity acts like a cosmic shepherd, deflecting or capturing these objects, preventing them from wreaking havoc on the inner planets. While some may see Jupiter as a bringer of chaos, it is, in fact, a guardian, its presence essential for the long-term stability of our cosmic neighborhood. Jupiter's atmosphere is a mesmerizing tapestry of swirling clouds, vibrant colors, and colossal storms. The Great Red Spot, a massive hurricane-like storm that has raged for centuries, is a testament to the planet's turbulent nature. This iconic storm, large enough to swallow Earth whole, is just one of many that churn across Jupiter's face, driven by the planet's rapid rotation and internal heat. Beneath Jupiter's swirling clouds lies a deep, mysterious interior. Scientists believe that the planet's core consists of a dense mixture of rock, metal, and hydrogen, compressed to unimaginable pressures and temperatures. This core is thought to generate Jupiter's powerful magnetic field, which extends millions of miles into space, influencing the movement of charged particles and creating a region of intense radiation known as the Jovian magnetosphere. Saturn, the sixth planet from the Sun, is perhaps the most recognizable planet in our solar system thanks to its stunning ring system. These rings, composed of countless icy particles ranging in size from dust grains to small moons, are a testament to the planet's gravitational prowess and the intricate dance of matter in the cosmos. While other gas giants also possess ring systems, none are as vast, as bright, or as visually captivating as those of Saturn. Like Jupiter, Saturn is a gas giant, its atmosphere composed primarily of hydrogen and helium. However, Saturn is significantly less dense than Jupiter, so much so that if a bathtub were large enough, Saturn would float on water. This low density, combined with its rapid rotation, gives Saturn a slightly squashed appearance, with a noticeable bulge at its equator. Saturn's rings are not a single solid structure, but rather a complex and ever-changing symphony of countless individual particles, each orbiting the planet like a miniature moon. These particles, composed primarily of water ice, range in size from tiny dust grains to chunks of ice several meters across. The rings are incredibly thin, averaging just a few tens of meters thick, despite their vast width, which spans hundreds of thousands of kilometers. The origin of Saturn's rings is still a subject of scientific debate. One leading theory suggests that the rings formed from the remnants of a shattered moon, torn apart by Saturn's immense tidal forces. Another theory proposes that the rings are primordial, leftover material from the early solar system that never coalesced into a larger body. Regardless of their origin, Saturn's rings remain one of the most captivating and enigmatic features in our solar system, a testament to the beauty and complexity of the cosmos. Jupiter and Saturn, with their immense gravitational pull, have played a crucial role in shaping the architecture of our solar system. Their gravity has sculpted the asteroid belt, a region between Mars and Jupiter, populated by millions of rocky remnants from the early solar system. These asteroids, ranging in size from pebbles to dwarf planets, are constantly nudged and tugged by the gravitational influence of Jupiter and Saturn, their orbits constantly shifting in a delicate cosmic ballet. The gravitational influence of these gas giants extends far beyond the asteroid belt. Their gravity has shaped the orbits of comets, sending some hurtling into the inner solar system and others flung out into the depths of interstellar space. Their gravitational pull has even influenced the evolution of the outer planets, shaping their orbits and, in the case of Uranus, potentially even tipping it on its side. While Jupiter and Saturn's gravity can fling comets and asteroids towards the inner solar system, they also act as a cosmic shield, protecting Earth from a constant barrage of cosmic debris. Their immense gravitational pull acts like a giant vacuum cleaner, drawing in and capturing many of these objects, preventing them from reaching Earth and potentially causing catastrophic collisions. The role of Jupiter and Saturn in shielding Earth from cosmic impacts is a testament to the interconnectedness of our solar system. While we often think of planets as isolated worlds, their gravitational influence extends far beyond their visible boundaries. shaping the trajectories of countless celestial bodies and influencing the very evolution of our cosmic neighborhood. Jupiter and Saturn, with their swirling clouds, colossal storms, and enigmatic interiors, remain some of the most mysterious and captivating objects in our solar system. Spacecraft like Juno, currently orbiting Jupiter, and Cassini, which spent over a decade exploring Saturn, have revealed unprecedented details about these gas giants, providing valuable insights into their atmospheres, magnetic fields, and internal structures. Despite these advancements, many mysteries about these gas giants remain. What lies beneath their thick cloud layers? What is the nature of their deep interiors? How did their ring systems form, and how do they continue to evolve? Answering these questions will require further exploration, pushing the boundaries of our technological capabilities and deepening our understanding of these enigmatic worlds. As we delve deeper into the mysteries of Jupiter and Saturn, we gain a greater appreciation for the diversity and complexity of our cosmic neighborhood and the intricate interplay of forces that have shaped our solar system. In the frigid depths of our solar system, beyond the familiar gas giants Jupiter and Saturn, lie the ice giants Uranus and Neptune. These two planets, often overlooked in the grand tapestry of our cosmic neighborhood, hold secrets that could unlock the mysteries of planetary formation and the evolution of our solar system. Unlike the inner planets, which are rocky and dense, or the gas giants, which are massive and composed primarily of hydrogen and helium, Uranus and Neptune are unique in their composition and characteristics. These distant worlds, shrouded in layers of icy clouds and whipped by supersonic winds, represent a different class of planet, one where water, methane, and ammonia dominate, shaping their atmospheres and influencing their interactions with the solar wind. The atmospheres of Uranus and Neptune are a complex mix of hydrogen, helium, and a higher proportion of ices such as water, ammonia, and methane. This unique composition gives them their characteristic blue color and contributes to the dynamic weather patterns observed on these planets. These icy behemoths, though faint and difficult to observe from Earth, hold clues to the formation and evolution of our solar system, their very existence challenging our understanding of planetary formation and the diverse range of worlds that populate our galaxy. The study of Uranus and Neptune provides valuable insights into the processes that govern the formation of planets and the migration of planetary bodies within a solar system. By examining the composition and behavior of these distant planets, scientists can infer the conditions that prevailed in the early solar system and the mechanisms that led to the formation of the diverse array of planets we see today. Uranus and Neptune, due to their vast distances from the Sun, receive only a fraction of the sunlight that bathes the inner planets. This limited solar energy results in extremely cold temperatures, with average temperatures on Uranus and Neptune hovering around -200 degrees Celsius. Despite these frigid conditions, both planets exhibit surprisingly dynamic atmospheres with powerful winds and storms that rival those found on the gas giants closer to the Sun. This dim illumination, combined with their icy compositions, makes them appear as faint blue dots in even the most powerful telescopes, their true nature shrouded in mystery until the dawn of the space age. The advent of space exploration allowed humanity to send probes and spacecraft to the outer reaches of the solar system, providing unprecedented views and data on these distant worlds. Prior to these missions, our understanding of Uranus and Neptune was limited to what could be gleaned from Earth-based observations, which were often hampered by the vast distances and the faintness of these planets. It was the Voyager spacecraft, launched in the late 1970s, that provided our first close-up glimpses of these enigmatic worlds, revealing their unexpected beauty, dynamic atmospheres, and complex systems of rings and moons. The Voyager missions were a monumental achievement in space exploration, offering a wealth of information about the outer planets and their moons. Voyager 2's flybys of Uranus in 1986 and Neptune in 1989 were particularly groundbreaking, capturing detailed images and data that transformed our understanding of these distant planets. Voyager 2's encounter with Uranus revealed a planet with a featureless pale blue atmosphere, punctuated by a few faint cloud bands and a curious lack of the dramatic storms seen on other gas giants. The spacecraft also discovered 10 new moons and 2 new rings, adding to the complexity of Uranus's system. The flyby of Neptune, on the other hand, showcased a vibrant blue planet with dynamic weather patterns, including the Great Dark Spot, a massive storm system comparable to Jupiter's Great Red Spot. Voyager 2 also provided the first close-up images of Neptune's largest moon, Triton, revealing a geologically active world with geysers of nitrogen gas and a surface covered in a mix of ice and rock. The discoveries made by Voyager 2 have paved the way for future missions to Uranus and Neptune, with scientists eager to return to these distant worlds to uncover more of their secrets. Proposed missions include orbiters and probes that would study the planet's atmospheres, magnetic fields, and internal structures in greater detail. Such missions could also investigate the intriguing moons of Uranus and Neptune, many of which remain largely unexplored and could harbor clues to the conditions necessary for life. Beyond Uranus and Neptune lies the Kuiper Belt, a vast region of icy bodies and dwarf planets that extends far beyond the orbit of Neptune. This distant region is home to a multitude of small icy objects, including Pluto, which was reclassified as a dwarf planet in 2006. The Kuiper Belt represents the outermost frontier of our solar system, a region that remains largely unexplored and holds the potential for many more discoveries. Studying the Kuiper Belt and its inhabitants can provide valuable insights into the processes that shaped the early solar system and the formation of planetary bodies. Even farther out lies the Oort cloud, a hypothetical shell of icy objects that is believed to surround the solar system at a distance of up to 100,000 astronomical units from the Sun. The Oort cloud is thought to be the source of long-period comets, which occasionally make their way into the inner solar system, providing a glimpse of the distant reaches of our cosmic neighborhood. While no direct observations of the Oort cloud have been made, its existence is inferred from the behavior of these comets and the distribution of objects in the outer solar system. The exploration of the outer reaches of our solar system, from the ice giants Uranus and Neptune to the distant Kuiper Belt and the hypothetical Oort cloud, represents a journey into the unknown. These distant regions hold the keys to understanding the history and evolution of our solar system, as well as the processes that govern the formation of planetary systems throughout the galaxy. As we continue to push the boundaries of space exploration, the outer reaches of our solar system will remain a frontier of discovery, offering new insights and challenges for future generations of scientists and explorers. Uranus, the seventh planet from the Sun, is a world of intrigue and peculiarity. Unlike any other planet in our solar system, Uranus spins on its side, its rotational axis tilted at an almost 90-degree angle to its orbital plane. This extreme tilt, the cause of which remains a subject of scientific debate, gives Uranus extreme seasons, with each pole experiencing decades of continuous sunlight followed by decades of darkness. This unusual orientation also affects Uranus's magnetic field, which is tilted at an equally extreme angle and offset from the planet's center, creating a lopsided and dynamic magnetosphere. Uranus's atmosphere, though composed primarily of hydrogen and helium like the gas giants Jupiter and Saturn, is distinguished by the presence of methane. This methane gas absorbs red light from the Sun, giving Uranus its characteristic pale blue-green hue. Beneath its serene exterior, however, Uranus's atmosphere is far from static. Voyager 2 observed faint cloud bands and even a few small storms during its flyby, suggesting that atmospheric dynamics on Uranus are more complex than initially thought. Beneath Uranus's thick atmosphere lies a deep interior thought to be composed of a mixture of icy materials, including water, methane, and ammonia. Unlike the gas giants, which are thought to have relatively small rocky cores, Uranus's icy interior is believed to extend for a significant portion of its radius. This icy giant structure, distinct from both the gas giants and the terrestrial planets, highlights the diversity of planetary compositions, and the challenges in neatly categorizing the celestial bodies that populate our universe. Uranus, like the other giant planets, possesses a system of rings, though these are far fainter and less extensive than Saturn's iconic rings. These rings, discovered in 1977, are thought to be composed of dark, icy particles, likely the remnants of shattered moons or captured comets. Uranus's rings, though faint, provide valuable insights into the dynamics of ring systems and the processes that shape these delicate structures over astronomical timescales. Neptune, the eighth and farthest known planet from the Sun, is a world of deep blue hues and powerful storms. Its atmosphere, composed primarily of hydrogen, helium and methane, is similar to Uranus's, but Neptune's methane content is higher, giving it a more intense blue color. Neptune's atmosphere is also far more dynamic than Uranus's, with powerful storms like the Great Dark Spot, a storm system comparable in size to Earth, raging across its surface. Neptune's extreme distance from the Sun makes it a world of perpetual twilight, with only a fraction of the sunlight that reaches Earth illuminating its atmosphere. Yet despite this dim illumination, Neptune's atmosphere is surprisingly active, driven by internal heat sources and the planet's rapid rotation. This internal heat is thought to be a remnant from Neptune's formation, slowly radiating away over billions of years. Neptune's dynamic atmosphere is a testament to the complex interplay of forces at play on this distant world. Its rapid rotation, combined with its internal heat source, creates powerful winds that whip across its surface, generating colossal storms that dwarf those on Earth. The Great Dark Spot, observed by Voyager 2 in 1989, was a testament to Neptune's turbulent nature, a swirling vortex of dark clouds that raged for several years before disappearing. Neptune's magnetic field, like Uranus's, is tilted at a significant angle to its rotational axis and offset from the planet's center. This unusual magnetic field geometry suggests that Neptune's magnetic field is generated by a dynamo process occurring in the planet's deep interior, likely within a layer of electrically conductive icy fluids. Neptune's magnetic field, though weaker than Jupiter's or Saturn's, still plays a significant role in shaping the planet's magnetosphere and influencing its interactions with the solar wind. Uranus and Neptune, though often overlooked in favor of their larger siblings Jupiter and Saturn, play a crucial role in shaping the outer regions of our solar system. Their gravitational influence extends far beyond their icy surfaces, influencing the orbits of countless icy bodies in the Kuiper Belt, a vast region of icy remnants from the early solar system that lies beyond Neptune's orbit. The Kuiper Belt, named after Dutch astronomer Gerard Kuiper, is thought to be the source of many short-period comets, icy bodies that periodically venture into the inner solar system, their tails blazing as they approach the Sun. Uranus and Neptune's gravity can perturb the orbits of these Kuiper Belt objects, sending some hurtling towards the Sun and others flung out into the depths of interstellar space. This gravitational dance, played out over billions of years, has shaped the population of the Kuiper Belt and influenced the frequency of cometary impacts on the inner planets, including Earth. As we conclude our journey through the solar system, we are left with a profound sense of awe and wonder at the intricate dance of celestial objects that grace our cosmic neighborhood. From the scorching heat of Mercury to the icy depths of Neptune, each planet we've encountered has revealed its own unique story, a testament to the diversity and complexity of worlds that exist beyond our own. Yet, despite their differences, these planets are bound together by an invisible web of gravitational interactions, their destinies intertwined in a cosmic ballet that has been playing out for billions of years. Our exploration of the solar system has revealed not only the unique characteristics of each planet, but also the profound ways in which these worlds have influenced the evolution of our own planet, Earth. From the protective shield of Jupiter, deflecting comets and asteroids that could pose a threat to life, to the gravitational nudges that shape the asteroid belt and the Kuiper belt, the fingerprints of our planetary neighbors are evident in the very structure of our solar system. The solar system, far from being a static collection of celestial objects, is a dynamic and ever-evolving system shaped by the forces of gravity, radiation, and collisions. Each planet, moon, and asteroid is in constant motion, influenced by the gravitational pull of the Sun and the other celestial bodies. This intricate dance of cosmic objects has been ongoing for billions of years, creating a complex and beautiful system that we are only beginning to understand. The Sun at the center of it all is the primary source of energy, driving the processes that shape the solar system. Its gravity holds the planets in their orbits, while its radiation influences their atmospheres and surfaces. The interactions between these forces create a delicate balance that has allowed life to flourish on Earth, while other planets remain barren and inhospitable. The planets we see today, their orbits, their compositions, their very existence, are all echoes of the chaotic and violent processes that unfolded during the solar system's formation some 4.6 billion years ago. In the beginning, the solar system was nothing more than a vast cloud of gas and dust known as the solar nebula. Over time, this nebula began to collapse under its own gravity, forming a spinning disk with the Sun at its center. As the material in the disk collided and stuck together, it formed larger and larger bodies, eventually giving rise to the planets, moons, and other objects we see today. This process, known as accretion, was incredibly violent, with countless collisions and impacts shaping the young solar system. The energy released by these impacts melted the surfaces of the forming planets, creating magma oceans and driving volcanic activity. Over millions of years, the planets cooled and solidified, developing the diverse landscapes we see today. By studying the planets, moons, asteroids, and comets that populate our cosmic neighborhood, we gain a glimpse into the early solar system, a time when our Sun was a young star, and the planets were still coalescing from a swirling disk of gas and dust. Each of these objects holds clues to the processes that shape the solar system, from the composition of their surfaces to the orbits they follow. For example, the presence of water ice on moons like Europa and Enceladus suggests that these bodies may have once harbored liquid water and possibly even life. Similarly, the study of asteroids and comets can reveal information about the early solar system's composition and the distribution of materials. These small bodies are often considered time capsules, preserving the conditions of the early solar system in their pristine state. By analyzing their compositions and structures, scientists can piece together the history of our cosmic neighborhood and gain insights into the processes that led to the formation of the planets. The scars of this early epoch are etched on the surfaces of planets like Mercury and Mars. Their cratered landscapes a testament to the bombardment they endured during the solar system's tumultuous youth. These craters, formed by the impacts of asteroids and comets, provide a record of the solar system's history, revealing the frequency and intensity of collisions over time. By studying the distribution and size of craters, scientists can infer the age of planetary surfaces and the history of impact events. For example, the heavily cratered highlands of the Moon are thought to be among the oldest surfaces in the solar system, dating back to a period known as the Late Heavy Bombardment, when the inner planets experienced a spike in impact activity. Similarly, the surface of Mars shows evidence of ancient river valleys and lake beds, suggesting that the planet once had a much warmer and wetter climate. These features provide valuable information about the early solar system and the processes that shaped the planets. The giant planets, with their immense gravitational pull, sculpted the asteroid belt and the Kuiper belt, shaping the distribution of icy and rocky remnants that continue to orbit the Sun to this day. Jupiter, the largest planet in the solar system, has a particularly strong influence on the asteroid belt, preventing the material there from coalescing into a planet. Instead, the asteroids remain as a collection of rocky bodies, ranging in size from tiny pebbles to large objects hundreds of kilometers across. Similarly, the Kuiper belt, a region beyond the orbit of Neptune, is home to a vast array of icy bodies, including dwarf planets like Pluto. The gravitational interactions between the giant planets and these small bodies have shaped their orbits and distributions, creating the complex structure we see today. By studying these interactions, scientists can learn more about the formation and evolution of the solar system, as well as the processes that govern the dynamics of planetary systems, and the very elements that make up our bodies, the carbon, nitrogen, and oxygen essential for life, were forged in the hearts of stars that lived and died long before our solar system was born. These elements were created through the process of nuclear fusion, which powers stars and produces the energy they emit. When these stars reached the end of their lives, they exploded in supernovae, dispersing their enriched material into space. This material then became part of the interstellar medium, the vast expanse of gas and dust that fills the space between stars. Over time, this enriched material was incorporated into new stars and planetary systems, including our own. The presence of these elements in our bodies is a reminder of our connection to the cosmos and the long and complex history of the universe. By studying the composition of stars and the processes that produce these elements, scientists can gain a deeper understanding of the origins of life and the evolution of the universe. The study of our solar system has profound implications for our understanding of life itself. As we gaze into the vast expanse of space, we are not just looking at distant worlds. We are peering into the very conditions that could foster life. Each planet, each moon, and each celestial body holds clues to the mysteries of existence. The more we learn about our solar system, the more we realize how interconnected everything is. From the smallest microbe to the largest gas giant, every element plays a role in the grand tapestry of life. By comparing and contrasting the conditions on other planets with those on Earth, we gain a deeper appreciation for the delicate balance of factors that make our planet habitable. Earth, with its perfect distance from the sun, its magnetic field and its atmosphere rich in oxygen, is a rare gem in the cosmos. Mars, on the other hand, presents a stark contrast with its thin atmosphere and dry, barren surface. Yet even Mars has secrets that hint at a wetter, more hospitable past. These comparisons are not just academic exercises, they are essential for understanding the potential for life elsewhere. The presence of liquid water, a stable climate and a protective atmosphere are all essential for life as we know it, and yet these conditions are by no means guaranteed. Earth's rivers, oceans and forests are teeming with life, supported by a delicate balance of temperature, pressure and chemical composition. Our atmosphere shields us from harmful solar radiation and helps regulate our climate. But what if these conditions were to change? What if our planet's climate were to become unstable or our atmosphere were to thin? These are not just hypothetical questions, they are real concerns that scientists are actively studying. Venus, with its runaway greenhouse effect, serves as a stark reminder of how fragile planetary climates can be. Once thought to be Earth's twin, Venus now stands as a cautionary tale. Its thick, toxic atmosphere traps heat, creating surface temperatures hot enough to melt lead. Volcanic activity and sulfuric acid clouds add to its inhospitable environment. Studying Venus helps us understand the potential consequences of unchecked climate change and the importance of maintaining our planet's delicate balance. While Mars, with its evidence of past liquid water, hints at the possibility that life may have once existed elsewhere in our solar system. The dried riverbeds and mineral deposits on Mars suggest that it once had flowing water, a key ingredient for life. Rovers and landers have been exploring the Martian surface, searching for signs of past or present life. The discovery of even microbial life on Mars would be a monumental breakthrough, reshaping our understanding of life's potential in the universe. The search for life beyond Earth is one of the most compelling scientific endeavors of our time. Scientists and researchers are dedicating their careers to this quest, developing new technologies and methods to detect life. Space probes are being launched to distant worlds, carrying instruments designed to analyze soil, ice, and atmosphere. Laboratories on Earth are simulating extraterrestrial conditions, testing the limits of life as we know it. This search is not just about finding life, it's about understanding the fundamental principles that govern life in the universe. And the study of our solar system plays a crucial role in this quest. Each planet and moon offers a unique environment, a natural laboratory for studying the conditions that could support life. Jupiter's moon Europa, with its subsurface ocean, and Saturn's moon Titan, with its methane lakes, are prime targets for future missions. These moons could harbor life in forms we have yet to imagine, challenging our understanding of biology and chemistry. By identifying potentially habitable environments such as the subsurface oceans of Europa or the methane lakes of Titan, we can target future missions and develop new instruments and techniques to search for signs of life, however simple or exotic it may be. These missions will require international collaboration, advanced technology, and innovative thinking. Scientists are already designing instruments capable of drilling through ice, analyzing chemical signatures, and detecting biological markers. The search for life is pushing the boundaries of science and engineering, driving innovation and discovery. The discovery of even microbial life elsewhere in our solar system would be a profound scientific breakthrough, fundamentally altering our understanding of life's place in the universe. It would suggest that life is not unique to Earth, that the conditions for life can arise in diverse environments. This discovery would have philosophical, ethical, and scientific implications, prompting us to rethink our place in the cosmos. It would inspire new generations of scientists, explorers, and thinkers, driving humanity to continue its quest for knowledge and understanding. The search for life beyond Earth extends beyond our solar system to the countless stars that grace the night sky.
Astronomers have now discovered thousands of planets orbiting other stars, many of them located within their star's habitable zone, the region where temperatures are suitable for liquid water to exist on the planet's surface.
These exoplanets, as they are known, represent a staggering diversity of worlds, some larger than Jupiter, others smaller than Mercury, some orbiting their stars in a matter of days, others taking centuries to complete a single orbit.
The study of exoplanets is a rapidly evolving field, fueled by advances in telescope technology and data analysis techniques.
As we learn more about these distant worlds, their atmospheres, their compositions, their potential for harboring life, we gain a deeper appreciation for the diversity and wonder of the universe and our place within it.
The search for life beyond Earth, whether in our solar system or beyond, is a testament to the enduring human spirit of exploration, our innate desire to understand our place in the cosmos and to seek out other life forms that may share this vast and ancient universe.
The exploration of our solar system is not merely an academic pursuit, it has tangible benefits for humanity. The technologies developed for space exploration, from communication satellites to medical imaging devices, have found widespread applications in our daily lives, improving our health, our communication, and our understanding of our planet. The study of other planets provides valuable insights into Earth's climate system, helping us to better understand and mitigate the effects of climate change. And the resources found on asteroids and other celestial bodies could one day provide valuable raw materials for industries on Earth and beyond. Continued exploration of our solar system is essential for advancing our scientific knowledge, developing new technologies, and inspiring future generations. By investing in space exploration, we are investing in our future, expanding our understanding of the universe and our place within it, and fostering a spirit of innovation and discovery that benefits all of humanity. The exploration of space has always captured the human imagination, inspiring generations of scientists, engineers, artists, and dreamers. The iconic images of astronauts walking on the moon, robotic rovers exploring the surface of Mars, and spacecraft beaming back breathtaking views of distant planets have ignited a sense of wonder and curiosity in countless individuals, encouraging them to pursue careers in STEM fields and to contribute to the advancement of human knowledge. By sharing the excitement of scientific discovery and the beauty of the cosmos with the public, we can inspire future generations to tackle the grand challenges facing humanity, from climate change to resource depletion to the search for life beyond Earth. Investing in space exploration is not just about advancing our scientific knowledge, It's about investing in our future, fostering a spirit of innovation and discovery that will benefit generations to come. As we venture further into space, we must do so responsibly and sustainably, recognizing that our actions have consequences for the delicate balance of our solar system and beyond. We must prioritize the protection of planetary environments, avoiding contamination of potentially habitable worlds, and preserving the pristine beauty of celestial bodies for future generations. We must also ensure that the benefits of space exploration are shared equitably among all nations and peoples, fostering international collaboration and cooperation in the pursuit of scientific knowledge. Our exploration of the solar system is a testament to the power of human ingenuity and our insatiable curiosity about the universe. As we continue to unlock the secrets of our cosmic neighborhood, we must do so with a sense of wonder, responsibility, and a deep appreciation for the interconnectedness of all things in the cosmos. The solar system, for all its familiarity, remains a place of endless wonder and discovery. Each new mission, each new observation, each new analysis reveals something new and unexpected, challenging our assumptions and expanding our understanding of the universe and our place within it. From the icy plumes of Enceladus to the swirling clouds of Jupiter, from the ancient riverbeds of Mars to the rings of Saturn, the solar system is a treasure trove of scientific wonders waiting to be explored and understood. As we continue to explore our solar system and beyond, we are reminded of the vastness and mystery of the universe and the countless wonders that await our discovery. The journey of exploration is never-ending, and with each new discovery, our sense of awe and wonder only grows stronger. The universe is ours to explore, to understand, and to marvel at, and the journey of discovery has only just begun.